Hello everybody and welcome back to my channel. Today this is a very special episode. We want to talk about the S3X Vertical. This is the most sophisticated jet of the whole project. And I want to invite you to come a little bit closer and we want to see all the insides. Some facts about the jet. The S3X Vertical was developed from 2016 to 2017 and the first hover was made in October 2017. Now that's 3 years ago and the first normal flight was done in June 2018. The transition tests started 1 month later. Also in 2018 the S3X Vertical take part at the VTOL World Meeting organized by the Dornier Museum. At this meeting there were several highlights for the S3X Vertical. At first, it was the first time I tried a vertical takeoff with direct transition to normal flight, and it worked very well. Second, I tried also the first vertical landing for the first time, and it didn't work, mostly caused of input mistakes by myself. I started shaking the jet, and when it becomes too steep, it crashed down vertical, as you can see in this small clip. But just the nose section of the jet get damaged, and I built a new one and everything is fine now. But at the end the S3X made the first place at this meeting. For me this was a very big motivation to go on with this project and bring it to perfection. To do the first complete VTOL pattern. This means start vertically, make the transition to normal flight, go one pattern, stop in the air and land vertically again. Hopefully this will be made next year. We are so close to this big leap. Then let's talk about the insides of this jet. So come a step closer and we want to open all hatches and see what is underneath. It's all complete electric powered and runs on a 8S LiPo setup with 5000 milliamps and 40C discharge. The VTOL concept is realized by two 90mm main EDFs. These are two Vemotec MIDI fans and they are 90-degree swiveling. The takeoff weight is 6.4 kilogram and the total thrust of this jet is 105 Newton. The thrust to weight ratio of the S3X Vertical in VTOL mode is about 1 to 1.6 and normal flight thrust to weight ratio is at the moment 1 to 1. The max current while lift up and transition rises up to 174 amps. The maximum hover time is at the moment 2.5 minutes with 20% rest capacity. Before we go more into detail of this jet, let's take a look to its forerunners. The idea to build a VTOL EDF jet was born shortly after the first successfully flights with the Styro SUX-47 in late 2013. After it became possible to fly very slow with high angle of attack by using a gyro, I want to make this jet stand still in the air. The first concepts were made, as you can see on these photos shown here. Fastly appears the fact that it will become very difficult to reach the goal with the present techniques. This means the battery and the engines. All components to realize this goal has to run on their best efficiency. So redirecting the airflow was no option because too much thrust will get lost. The only option was to swivel the complete engine so that they can perform as best as possible in VTOL and normal flight. Here you can see some footage of the first prototype VTOL jets. At first all engines are 70mm EDFs, but it became clear that in this setup the performance in normal flight is too bad. So the whole concept was amplified, and 90mm EDFs, like in here, were used as main engines. At last, it emphasizes that the styro construction itself was too unstable and too heavy, beside a lot of aerodynamic disadvantages. And this was the moment the S3X project was born. So, okay, let's come over and take a look at the S3X vertical. We had open all hatches, and we will take a direct look to see what is underneath. At first, we take a look at the front fan. You can see it here. This is a 70mm EDF with 20 Newton thrust. It is stabilizing the jet on the lateral and vertical axis. To realize this, there are two vanes installed underneath which direct the airflow to the left and right side. Next are the canard servos. You can see here. They move the canard and the elevator. Both are coupled via a push rod. And now we come to the heart of the whole jet. These are the two 90mm main engines, and as I told you, they are sweepable for 90 degrees. And this we want to show you now how it works. You can see here, now they are in normal flight condition, and this is for the vertical start and landing. So you can see the main engines here, and they can swivel 90 degrees. Now they are in normal flight mode, and so it looks like when they lift up the jet vertically. Let's go to the RC compartment. Here is all the electric and the controllers installed. We have the receivers, the telemetry transmitter, and also the gyro for the deflection surfaces, and the KK board for stabilizing the S3X vertical while hovering. And we have the BEC and also a weak cable. At first we have the iGyro. This is the blue one, and the iGyro stabilizes the jet while normal flight. It moves all deflection surfaces. You can see this very good in the small video. While flying, especially the rudders and the elevator is always moving a little bit to keep the plane stable and still in the air. Because the S3X is a dynamically unstable jet, and it is very difficult to fly it without the help of such a gyro. But with this gyro, it feels like a beginner jet. It flies very easy, but all the time, all the deflection surfaces has to move and stabilize the jet artificially. The next is the hover flight controller. This is the KK board. It controls the 3 small lift fans and stabilizes the jet around all 3 axes while hovering. And we also have this small controller underneath here. This is the SM V cable. And with this small controller, it became possible to switch into VTOL mode by using only one channel of my transmitter. And it makes it very easy to adjust all the settings for the servos, for instance, of these doors, and also the way of travel and the delay. We want to show you now how this VTOL mode works completely. Okay, and now let's go to the side fans. These 2 fans. They are installed into the wings. They are especially designed for the S3X vertical. They have a diameter of 70mm, but they are just 36mm high. The weight of them is about 100 grams, and the thrust is 10 Newton. Here I do have the side fans separately, This one is without engine. The engine is inside the fan installed. Here is the engine installed, so that they can build as flat as possible. This fan has already the engine installed. Yeah, you can see here this red shiny metal is the engine, and this is how they looks like. On the rear open hatch we can see the vector nozzle servos. These are these 3 tiny servos, and they will move these nozzles like I show you now. We got the rudder servos inside the vertical fins and also the satellite transmitters. One satellite is installed in every vertical fin. Here we can see the canard servo, and this servo is moving the canard and also the elevator. They are both combined rear push rod. Here you can see how it moves. And now we want to see how the VTOL mode is working. For this I will start the KK board. So now the white light is blinking. This means everything would be ready for vertical takeoff, and I switch into VTOL mode. Now the engines are running and the jet foot lifts up. So now we want to talk about how this jet was tested before the first transitions were made. It is very dangerous in flight to do these transitions, so a lot of things has to be tested at the ground. For instance, if these lift fan doors are stable enough and they don't flew off while they are working in the air. For this we have an EDF, a 90mm EDF installed here, which produces an airstream with about 100 to 200 km per hour, and this flews over this door and brings air forces on this door. And let's see if everything works. Now I will bring the jet into the VTOL mode so that the door opens, and now we start with the airstream of this fan and see what happened. You can see the door is shaking, but it is closing and everything is fine. Now we did this test. We produced this very strong airflow along this side vent door, and we saw that the door was shaking a little bit, but everything works fine. The servo was strong enough to open the door and close it again. So this test was successfully, and with this small, let's say, wind tunnel, outdoor wind tunnel, all doors had been tested, also the deflection surfaces, if the servos are strong enough to work also in the air, while we have this real air forces when the jet is flying. The jet flies up to 200 km per hour, and at this speed, you know, if you hold your hand out of your car while 200 km, the air forces are getting very strong, and everything in this jet has to be strong enough to withstand these forces. At last, I want to say some words to the actual stage of affairs. The SUX Vertical did almost about 200 takeoff and landings and about 100 transitions. One vertical takeoff was made with a direct transition into a horizontal flight, and it worked successfully. The last step is a complete vertical pattern. This means vertical takeoff, transition into normal flight, stop in the air, and land again vertically. And this last step, to stop in the air and land vertically, is the very last thing this jet has had to do. And I think this should be possible in the next year. I hope you have enjoyed this video and take some notice of this jet, and see you in the next video. Bye bye!